In today's class, we shall discuss particularly the software for embedded systems and in particular the software environments and the practices to be followed for developing softwares for embedded applications. So, embedded software are typically hidden in watches, VCRs, cellular phones, toasters, and they are not like a general purpose software. It guides missiles, controls satellites, also used in medical instruments. So, obviously, this application scenario makes embedded software special and different from that of standard desktop software. You have varying requirements and the characteristics of hardware platform is also different, because we have already understood the hardware aspects of embedded systems. In a way, the software for embedded systems interact with physical world. It therefore definitely takes time. So, there is an issue of time consumed by the software in relation to the timings of the external events. It consumes power. So, we have to think in terms of designing software which is power efficient. The last thing is that it does not terminate. Unlike standard programs where we expect them to terminate in finite number of steps, these programs typically do not terminate. What are the requirements of software for embedded system? Reliability, because human intervention is not possible for error handling. They are expected to run without human intervention for a long period. They should be cost effective, low power consumption, they should make efficient use of memory, because the memory cannot be unbounded, and the performance requirement, the most important performance requirement is that of timeliness. So, on the basis of requirements, what kind of features do we expect in embedded software? The most importantly, timeliness. Computation takes time. Even if we have got infinitely fast computer, embedded software needs to deal with time, because the physical processes with which it interacts evolves over time. So, these timing conditions and constraints are to be followed. And the other important issue is that use of elaborate caching schemes, speculative instruction execution, branch predictions, these are avoided in microcontrollers and DSPs which are targeted for embedded applications, because they may compromise system efficiency. In fact, last time we have seen that these hardware features can lead to additional power consumptions. Okay? So, we have to design software such that these timing constraints are met, and we really do not have these special hardware features for speeding up the software. The physical processes are concurrent. So, concurrency is a very important issue in relation to embedded systems. So, embedded systems need to react to stimulus from a network of and a variety of sensors and retain control over actuators, and so the processing should be concurrent. Related to concurrency is the issue of liveliness. Programs must not terminate or block waiting for events that will never occur, because if it gets blocked in such a way, then the whole system would basically fail. So, in fact, watchdog timer is one of the hardware features which can be used to ensure liveliness. Next issue is that of interfaces, because when you build up a software, you have to do a kind of a composition, a reuse of the components. So, if you go back to the basic object oriented framework, we can do reuse via inheritance or via composition, and these composition are particularly at the level of static behavior. In terms of dynamic behavior, if you are talking about processes, then the issues comes up as how to combine the two different processes so that they can work in a cooperative fashion. Okay? And the other important issue is that the combination of the software which is coming from various sources, maybe third party software, and how you can safely combine them with the existing software. The issue of security, correctness of operation for these kind of composition is a important feature for embedded application. Since you are getting softwares from different sources and also you need to deal with external events which are of different nature, heterogeneity becomes an important component. If you consider a simple mobile phone, the job of receiving the speech data in a compressed form, decompressing and playing it back has got a characteristic different from that of accessing your phone book. So, these are two different types of computations and these two computation styles have to be handled together. And also the events which occur in the external world may be of different type. They may be regular, they may be irregular, okay? And your software needs to handle both kinds of event without unnecessary delay. In a way, what we are talking about is reactivity of the software, which is of fundamental importance for embedded systems. It should react continuously to the environment at the speed of the environment. If it cannot react at the speed of the environment, then the whole situatedness of the appliance gets diminished. Okay? So, the whole importance of dealing with external events as they occur makes embedded system so powerful. So, reactivity is an important issue with embedded systems. They should be also safety critical, because in many cases they are handling a critical equipment or critical machinery. Okay? So, they cannot fail arbitrarily, okay, or fail without giving prior signals such that a catastrophe occurs. So, there have to be built in safety critical features with the software. We are so far talking about that reactivity. The reactivity means reacting to the external environment, and since it is reacting to the external environment, obviously there will be bounds in the response time. Okay? So, formally there would be a response time bound, and what is really a response time? The time between presentation of a set of inputs to the system and realization of the required behavior, including availability of associated outputs. So, this is what is response time. So, when there is an external signal coming in, corresponding to the characteristics of the external signal, there will be bound on the response time, and that leads us to the formal definition of a real-time systems. A real-time system is a system that must satisfy explicit bounded response time constraints or risk severe consequences including failure. But one point also to be noted, that all embedded systems are not necessarily real-time systems. Okay? There are some systems which are definitely real-time, and for them this bound is critical. These real-time systems can be categorized further. We talk about soft real-time systems and hard real-time systems, as well as firm real-time systems. A soft real-time system is one in which performance is degraded but not destroyed by failure to meet response time constraints. It may be an automatic teller machine, there may be delay in delivery of the cash or delivery of the receipt, but that delay is not critical. This is true for a typical DVD player as well when it is decompressing a video frame for playback. In fact, in a way you can consider that all systems or all software for that matter in some way or other soft real time, because you won't like to use a word processor which would give you a response time of say 5 minutes. Okay? So, there is also a kind of a minimum expectations for the interactive systems. A hard real time system is one in which failure to meet a single deadline may lead to complete and catastrophic system failure. Okay. So, example is say avionics weapon delivery system, because after the decider presses a button to release a weapon, okay, from that point to the actual delivery should be bounded, otherwise the target would be missed. So, the whole purpose of releasing the weapon is lost. So, this is a hard real time system. The other example could be a control system in a nuclear power plant. A valve has to be closed within a definite bound, otherwise there may be an explosion. A firm real time system is one in which a few missed deadlines will not lead to a total failure, but missing more than a few may lead to complete and catastrophic failure. So, it is somewhere between hard and soft real time systems. An example is a navigation controller for a robo weed killer. This is slightly a different kind of an example. So, if a robo weed killer is moving around, there will be deadlines corresponding to its navigation. It can miss few deadlines, okay? But if it continues to miss the deadlines, what can happen? It may actually destroy the good crops instead of the wheat. Okay? So, the effect can be really catastrophic. Now, how do you measure quality of such software? What is dynamic efficiency? That is number of CPU cycles required for execution of the software. The other part is the static efficiency, that is the number of bytes required, okay? The RAM size, the ROM size. The RAM would accommodate the variables and the runtime stack as well as the heap. The ROM size would determine the fixed constants and the program code. ROM we are using in a generic sense, it can be EEPROM, it can be E2PROM, it can be even flash. And the power consumption is another issue. So, these three are very important parameters to measure quality of a software targeted for embedded application. The other issues, the obvious is correctness, logical correctness as well as temporal correctness. And these two are primarily for the purpose of maintaining and reusing the software. So, it should be easy to understand, it should be easy to change, so ensures flexibility and maintainability. These are more from the classical software engineering perspective. So, what is the process of developing a software for an embedded system? It would be very similar to that of a general software, but there may be and there will be some differences. First, you obviously determine the requirements. You design the system architecture, the software system architecture. With respect to the requirements of the system architecture, you select operating system. It is not that for all embedded systems you really require an OS. If you really require an OS, what kind of characteristics the OS should satisfy? Then you choose the development platform, because the development platform is in many ways dependent on the OS that you choose. Then you obviously code the application, optimize the code according to the requirement. You should optimize the code so that you can meet the quality measures. Verify the software on the host system, it may be simple simulation, and then verify the software on the target system. So, what are the different choice of programming languages that you can use for developing the software? It may be assembly language, it may be high level language. If you are using assembly language is obviously processor dependent. An assembly language program can be really efficient because you can exploit the architectural features of the target processor directly. But it is difficult to maintain and write large programs, because then it becomes complex, because the number of instructions that would be required will be much more. As the number of instructions increases, the probability of bugs coming into the code also increases. At the same time, the other problem is portability, because if you decide to change the processor, then your software has to be completely changed. High level language obviously ensures portability and easy software development, because the number of instructions, the number of lines of code that you need to handle for a given task could be much smaller. And the compiler performs the job of translation. But compiler may not have the capability to optimize the target code with reference to the target architecture. So, if you look at the basic programmer's view, what we find today, the most development is done today using structured languages, that is high level languages, but some assembly level programming may still be necessary. In particular, the device drivers, the portion of program that communicate with or controls another device which is connected with your basic microcontroller. For those device interfacing applications, you still need to do assembly language programming, because you have to take care of very strict timing constraints and may involve extensive bit manipulation. So, for that purpose, assembly language program is pretty efficient. So, therefore, the software development goes through what is known as a build process. Now, when target platform is known, tools can exploit features of the hardware and the OS in the building process. But it is not always that you can make assumptions about the target. So, in that condition, user needs to provide information about the target. So, the build environments which are targeted for these kind of developments always have provision for putting in these kind of parameters from the users. The most important aspect or the component of the build process is compiling. Okay. And the compiling is important here. That aspect of compiling is important is the object code generation and what we call code optimization. Because the object code has to be optimized with respect to the target architecture, and you need to optimize also the code that you are generating. You cannot really translate straight away a high level language code into the target machine instructions. There has to be some kind of code transformations if we want to optimally exploit, say, the register set of the processors. Okay. So, that aspect of compiler design and implementation is of tremendous relevance and importance for embedded systems. Then other important issue is that you actually use cross compilers or cross assemblers. These compilers or assemblers actually runs on host, which is different from the target. Typical standard compiler, a C compiler in a Linux machine, you will run and generate the code for the target architecture itself. The target architecture may be the Pentium itself. But when you are using a cross compiler, it may run on a Linux machine, but it would generate the code for, say, ARM processors. Now, what does compilers generate? Compilers generate object files. Contents of object file can be thought of as a very large flexible data structure which contains instructions and data resulting from the translation process. So, the object file is not directly executable image. Okay. So, object file which is generated in the host system is not definitely the executable image. They come in standard forms. Okay. These are common object file format, COF, ELF, extended linker formats. Why they come in standard form? Now, these object files can be used with the linkers or the software tools which are targeted for the specific platforms for generating the executable image. So, object files typically contains code blocks which are text block, which we refer to as text block, initialized or even uninitialized global variables, which is a data block, and usually the symbol table, and this symbol table is used in many cases for debugging the software. Next comes the linking. The next important process is linking, because you can have the compiler compiling individual modules and generating the object code. So, linking is basic process of merging sections from multiple object files. The unresolved reference to symbols are replaced by reference to actual variables or function calls, okay, because these references to the variables may be to modules external to the current module, and they are to be bound to correct relative address. A special object file that contains compiled startup code is included. Okay. So, what is this startup code? Startup code is a small block of assembly language code that prepares the way for execution of the code. In fact, this is typical to that of an embedded systems. Because see, when you are linking the different modules, you have resolved the address references, you have resolved the address references with respect to the relative addresses. Okay. But now you have to initialize the system to get the code running, and that code is typically your startup code. So, a startup code usually consists of following actions in a sequence. You disable all interrupts typically, copy any predefined data from ROM to RAM, okay, zero the uninitialized data area, allocate space and initialize a stack, initialize processor's stack pointer, create and initialize the heap, execute constructors and initializers for global variables for object oriented languages like C++, enable interrupts and then call main. So, what does all these things mean really with regard to an embedded target platform? So, you are basically preparing the environment for the software to run. Many of these jobs typically will be done on a general purpose computing platform by a loader, okay, but you really do not have a loader in this case. You are directly loading the software onto the processor's memory or the target board's memory for the purpose of execution. Okay. So, the startup code can include all these features, because for execution of a program, what do you need? You need stack to accommodate local variables as well as the return addresses. So, stack needs to be initialized. For dynamic memory allocations, you need heap. So, heap is also to be initialized. What does that mean? It means basically allocating memory areas which are to be used for heap area as well as stack area, and the area in which actually the program would really reside. Okay. Why you disable interrupts? Because until and unless these parameters are set, you cannot possibly service the interrupts, because interrupt service routine may be part of your code. In fact, this is typically done for an initialization of a system. In fact, for a raw system, a programmer may need to write his own startup code and link. If a programmer is using a target OS on the target board, the OS may supply the corresponding startup code. And please try to understand one very basic issue is that you will be loading OS with specific functionality and not with general purpose functionality. Okay. So, the startup code which comes with the OS needs to be linked with the softwares that you are developing along with the modules which may come from the OS to develop the complete software environment for the target embedded system. You also have what is called a locator. Locator is what is bundled together with the linker. Now, designer provides information about the memory on the target board via the locator, and locator uses this information to assign memory addresses to code and data sections. In fact, GNU linker has this provision that can be passed to GNU linker in the form of a linker script. So, you need to know the memory map of the target board. Okay. Your host system where you have actually done the linking does not know it. The linker has also done the job that of a relative address resolution. So, this locator gives you the memory map. So, you can actually create the memory image, fine, and you use along with this the startup code, because now startup code exactly knows how the memory has to be partitioned between stack, heap as well as the program code, and then you load the complete bundle on the target board for the purpose of execution. So, the one very basic issue is that of memory allocation for any kind of software environment. One is global variables, because a program when it is in execution, okay, it got to have the global variables, got to have the heap for dynamic memory allocations. In fact, for an object oriented language, the objects are also allocated in heap. You have got stack for local variables, return addresses and temporary data, and this content changes in runtime. So, the RAM memory is distributed among these components, and if you can estimate the size of these components beforehand, that will determine the size of RAM that you actually require on the target board. The ROM memory has the machine codes as well as the fixed constants. If you have both ROM and EEPROM, okay, partitioning depends upon the requirements of the design, okay, because the configuration data can be typically put in ROM, okay, and your software can go in an EEPROM which can be modified or updated. The flash can also have your basic software, but in many cases flash can be used for a data store. Say a typical camera application, you would like to have the images stored in the flash, and flash is slower compared to RAM, and if in ROM we have found is slower compared to RAM. So, we have seen that RAM is used to shadow code or parameters to improve performance. So, typically it is copied from ROM or flash to the RAM if that is containing your program code. So, it is faster in terms of access. So, running a program is if development processor is different from the target, you download to the target or you simulate. This is the two basic things, and the basic process of exercising a code is run on the host system. So, run on an instruction level simulator, cycle accurate simulator, run in hardware software co-simulation environment where you are simulating hardware components as well. Once you are satisfied about your software in this environment, then you go to the target system. In fact, when you are actually going to this target system, then this locator as a system programming component, as a system software, as well as your startup code becomes critically important. Next, we look at the issues related to development of program in high level language for embedded systems. Now, all of us know the basic programming, okay, all of us know the basic programming techniques and tools. What we shall look at here is that these different mechanisms which are available in high level language, what are their implications with reference to embedded systems. So, let us look at parameter passing. If you look at call by value means the value of the variables are actually copied to the stack. So, there is always a time cost, okay, but and that is why you will never find that large data structures are never passed by value. You actually pass on a pointer is passed by value. But if you are passing by value, that is called by reference, the problem is you have to use indirect addressing modes for accessing the variables. Since you are using indirect addressing modes, you are paying in terms of time for execution of a code. So, if you need to optimize in terms of timing parameters, you may need to decide which mechanism to be followed for parameter passing. So, there are trade-offs, and these trade-offs are to be balanced for deciding on the mechanisms to be followed. The global variables and parameter lists. See, global variables, references to the global variables will be definitely faster because you can do a direct addressing to global variables, but parameters make interfaces clearly defined, because if you are using only global variables, then if the global variables gets modified, there can be side effects and that can introduce a bug. So, that is why the global variables from the purpose of software designs are to be avoided, but they provide you the fastest mechanism for communication. Okay. So, if you are really pressed for time and time deadline, you may need to resort to global variables. Recursion is something which should be avoided, fundamentally because recursion requires what? Indirect addressing. Also, you really do not know the memory requirement beforehand. The memory requirement in runtime you cannot really assess beforehand, because that would depend on the recursion depth. So, it is always desirable that when you are writing a software for embedded applications, you replace recursion by iterative constructs. So, you really know that the number of times that will be executed. So, you have a more deterministic memory requirement assessment. The other issue is that reentrant procedures. A reentrant procedure can be used by several concurrently running tasks in multitasking systems. And if you really have a multitasking system, a basic requirement is that procedures must be reentrant. What does reentrancy imply? It implies that if you are writing such a procedure, you should take care to save the state of the processor. That means all the registers as well as the variables that are being used. These variables cannot be in an arbitrary memory locations. All variables must be, local variables must be in the stack, and all registers must be stored in the stack, okay, before this procedure starts execution. And once you come out of that procedure, these state must be restored back. This makes sure that if the same procedure is invoked by another concurrent process, that same procedure can be used by another concurrent process without disturbing the data of this procedure's invocation by the original thread. So, a very simple example could be if you are using an editor, say VI editor in a Unix system, there could be only one VI editor running and each user can use different files to edit upon. Okay. Since the program or the procedure is designed in a reentrant form, there won't be any conflict, and there may be multiple VI editors or multiple versions of the same procedure running in the context of multiple concurrently running tasks. The dynamic allocation, that is dynamic memory allocation, provides flexibility in construction and maintenance of data structure in runtime. And in fact, many cases we need to use these kind of data structures, but obviously the allocation is time consuming, okay, and the same issue can come back that if you really do not have an estimate on the upper bound, you may run out of the heap area allocated to a process at some point in time, because you are expecting your program to do what? Run continuously. Okay. So, this management of the dynamic memory becomes a critical component there. Typing is an issue. Strong typing can prevent unwanted change in the data through truncation or rounding, but say a weak typing permits expressions of mixed type. Say take for example a C expression. In a C expression you can use integer, double, float at the same time. And what happens if you using the mixed types, the whole evaluation takes place in the double form. That means all variables are converted to the double form, and then depending on the type of the variable to which you are assigning the value will be rounded or truncated depending on the policy followed. But this obviously gives two issues. One is, since you are converting them to a double, you require higher storage requirement during computation. So, you need to assess that whether that kind of a memory would be really available or not, and there would be unseen and time consuming instruction for type conversion, which you might not have computed when you have done the basic assessment, okay, source level assessment. Only a proper profiling would really give you the kind of timing which may be required. What is profiling? Profiling tools would give you a kind of timing requirements or time being consumed per procedure or block of codes, number of times a procedure being called, a number of times a block of code being executed. Exception handling is another important feature, and in fact today you find that all major languages, even ANSI C, since it is targeted for embedded and other applications, ANSI C also gives you a provision to deal with signals. So, these are exceptions. There can be variety of exceptions, and there should be exception handler codes, okay, because if you cannot handle exceptions, the system can go into an undefined state. So, exception handling for embedded systems is important, and that makes the software what we say dependable. The programming languages are all we familiar with: C, C++, Java. Now, if you look at, I have just picked up 3 samples. In fact, ADA is also being used for embedded software developments, ADA 95. C is very widely used with functionality because it has got various constructs which is similar to that of an assembly language constructs. You would like to go for an object oriented language because of its reusability of any of the design components. The reusability comes in terms of composition, because you can build an object by combining the objects which have been already designed. Also, reusability comes through inheritance. And Java satisfies this object orientation, but at the same time the interest in Java is because of the code mobility. Because the Java virtual machine is a representation, in fact it is nothing but a kind of a code simulator, an instruction level simulator of a target machine architecture which can run in a platform independent fashion. In the sense that you have got for each OS or target architecture the JVM implementation, and when you write a Java code and you compile it into a bytecode, that bytecode is suitable for executing on the Java virtual machine. So, if you have with the OS a Java virtual machine which is matched with the hardware requirements as well as that of the OS, you can have same code downloaded onto variety of embedded systems and execute it. So, in fact, Java gives you a very interesting feature. We typically find that the software for an embedded system is a closed software, that once you have developed the software and deliver the product, software is constant. Okay? But Java gives you another interesting feature, is that because of its portability of your executable code, you can get the software from third party sources and enhance the functionality of an embedded system. That makes Java as an attractive programming vehicle. So, use of C is obviously the reason what we had already talked about, because of various processor dependent definitions of objects like characters, bytes, bits, addresses can be handled directly. You can have a bit vector, and using the bit vector you can do variety of operations. Even in many of these C variants supported by the embedded processors, that is development environment of embedded processors, you have got structures defined in terms of bit vectors. So, in a bit vector you can have fields of fixed bit length, and you can do manipulation with the fixed bit length. C also provides special variable types, in fact storage types, not really types in terms of the data type, storage types like register, volatile, static and constant, and in fact these helps in various kinds of software developments. So, if you look at register variables to be frequently used, compiler places in a register. So, this is a directive to the compiler to generate optimal code. In fact, this is a, because compiler is not really able to understand completely your code, the intention of the code, the usage of the code. So, that way register, if you mark a variable register, it is a directive or a suggestion to the compiler to map it to the registers of the target processor. Static is a private communication in modules. In fact, static retains the value beyond invocations, because a local variables in a procedure will lose the value the moment you are out of the procedure, but static retains the value. So, it is stored globally, and so you can have encapsulation, that is in terms of the private value which is not visible outside, but you can carry on the value from invocation to invocation. So, volatile is useful for handling memory mapped IO which need not be optimized. In fact, the basic issue is that if you are using a memory mapped IO, I discussed this point earlier also, ideally you should not map those memory locations to cache, okay, because they can be changed by external devices. So, if you look into this, that for memory mapped IO, a byte at some memory address may really represent the status of a printer, and printer updates that byte. If this corresponds to a variable in your C program, then that variable may be changing. Okay. A problem occurs with caching. Suppose that value is placed in the cache. Now we have a copy, but the I/O device is updating what would be considered memory and not the cache directly. So the value in the cache and that in the memory are not the same. Okay. One way to have the compiler avoid caching is to use volatile keywords. In fact, compiler does not avoid caching, but compiler generates a code in such a way that the caching would be avoided for those data structures. Okay. A variable that is volatile is expected to change outside the program's control, thus it should not be kept in cache because the cache may not see the updates. So, this storage type specification you can understand is important, because say today if ARM is one of the most popular 32-bit processor, ARM supports only memory mapped I/O. So, with reference to that kind of an architectures, this consideration becomes important. Memory management in C, it can obviously support static allocation. The global variables are really allocated during compile or link time and actually can increase the code size, because these memory areas are form part of the code. The other variables, the most commonly used variables are automatic allocation. They are allocated at runtime in stack. Okay. Compiler provides support for allocation and access to these variables. So, these variables really do not form part of the code. So, if you are estimating the code size, if you are trying to estimate the memory requirement by looking at the compiled code size, that will not be correct, because automatic variable sizes will not be part of that. So, that estimation has to be done separately. And the dynamic memory allocation, allocation at runtime on demand, and allocation and deallocation under program control. Typically, you will be using malloc, calloc for allocation and free for releasing this memory area. This allocated memory is allocation where in heap area. So, the memory in heap is organized typically in chunk of 16 or 32 bits, 32 bytes typically, or there may be other sizes as well. So, memory is actually acquired or released in units in which this memory is divided. Now, obviously, this can lead to an wastage of memory, because if you are allocating a data structure or a structure of size 4 bytes, then you would be wasting 12 bytes if you are allocating by units of 16. Okay. And that is a wastage because of what we call internal fragmentation. Why this fixed chunk is used? For maintaining the heap as a data structure, for keeping track of free memory area in the memory for the process. So, the smaller unit size minimizes obviously this wastage because of internal fragmentation, but increases memory requirement for maintaining data about the allocated blocks. Because what is really heap? We talk about stack and we talk about heap. What is really heap and stack? Your memory is not getting organized in form of a heap or a stack. You are keeping a data structure. Say in case of a stack, you are using a stack pointer for accessing an area of a memory following stack discipline. For a heap, you have a memory area. Corresponding to that memory area, you are maintaining a heap to provide access to the free blocks in that memory area. Okay. So, what is a heap? Heap is nothing but a tree. Okay. And you are using that, keeping that data structure. So, if you have smaller unit size, that memory consumed by that tree itself becomes large. Now, these issues are not very important if you are looking at a standard computing platform using maybe 2 GB of RAM, okay, along with the facility for virtual memory. This becomes important when you are looking at an embedded system which may be using just maybe 64 MB of memory, or maybe just 256 MB of memory. These are all on a higher side. So, real-time OS provides support for programmer defined unit size to optimize memory usage, because if you are wasting a memory, then that memory, you are wasting a memory at the same time. That is why you have to use bigger memory. Bigger memory means more energy consumption. So, real-time OSs, or the OSs which are targeted for embedded applications, they gives you a facility and the feature to decide on this unit size for the heap. Okay. And heap is organized in terms of say decreasing size, increasing size, or adjacent block. So, typically what it means, if it is in terms of a decreasing size, the root node of the heap would be pointing to the largest free block available in the heap. Free returns unit to heap. Now, when you are returning the free, the type of the pointer, if you are using C, becomes important and critical. Why? Because on the basis of the type of the pointer, the runtime environment knows what is the exact size of the memory which is to be freed and put back to heap. And if you are using a free on the same variable more than once, what can happen? You have freed a memory area, then that memory area might have been allocated for some other data structure, then again you are freeing it. So, that memory area going back to the heap, and that may give rise to an inconsistency, okay, and a fault which may surface later on. So, overhead in a heap management, so what you have, you pay for two kinds of overhead. Overhead for search in a heap for a requested allocation, overhead for compaction. Now, adjacent units are coalesced for creating larger free chunks and can take unknown period of time and violate real time constraints, because when you compact the different blocks together to get and create larger memory chunks or memory areas, it may be really time consuming. A fundamental problem with dynamic allocation, which is of importance for embedded systems, is called memory leak. Memory is allocated, but not properly freed. So, this memory is not available subsequently, and since your program is running forever, then this error can surface subsequently at some point in time. So, what would it mean? A malloc is returning a null pointer. So, this memory leak is a very important problem in the context of dynamic memory allocations. The other problem is that of a dangling pointers. Okay. What is meant by dangling pointers? Pointers referring to memory locations which have been freed. Okay. So, it may be used in the context of other data structure. So, if you are using dangling pointers, you may corrupt other data structures and may create problems. So, a pretty strict discipline is to be followed while using dynamic memory. The other language, say object oriented language, is Java, and I told you that Java is interesting because of the portable feature it has got. It supports various features of object orientation, and a very interesting feature is that of automatic garbage collection, because it is an object oriented language. The object gets allocated in the heap area, and these objects have to be freed if we have lost reference to that object. So, it has got an automatic garbage collection. This garbage collection task gets scheduled automatically for removing these objects, and that is freeing these objects. So, what does that imply? It implies that your code gets suspended and garbage collector gets executed depending on the time when the garbage collector is scheduled. It has got exception handling mechanism. It also supports multi-threading. Now, some version of Java, there is one version of Java which is called Java 2 Micro Edition, which is targeted for consumer appliances and embedded systems. In fact, your Java compliant mobile phones, PDAs, they do support J2ME versions and not really full fledged Java. Okay. And they addresses J2ME two types of devices, what we call connected device configuration, typically set top box, internet TV, etc., where you have memory capacity between 2 to 16 MB, and other is connected limited device configurations, typically mobile phones, pagers, PDAs, which are connected to low bandwidth network and having capacity between 128 KB to about 512 KB. In fact, the basic assumption is that your processor is a 16 or 32 bit processor with a clock speed starting from approximately 12 to 32 megahertz with a memory budget for Java virtual machine and libraries of about 512 kilobytes. Okay. So, this Java virtual machine is nothing but a software which is involved in execution of your code, and that size has to be restricted. So, this is typically 512 kilobytes. In fact, in context of J2ME, the Java virtual machine is called KVM or kilobyte virtual machine. Architecturally, it is something like this, that you have got in a CLDC, you have got the KVM, Then on top of that, the J2ME CLDC libraries that constitute the core runtime environment. Then on top of that, you have got profiles. Profiles are device specific in many cases. You may have a handheld profile, and these together gives you the runtime environment. Now, this is for your CDC, which is larger. So, you have the JVM, Java Virtual Machine, which is similar in capability as that of your standard edition, and you have got the profile on top of that. Smaller than that is Java Card, which is targeted for smart card applications. You can have Java code running on smart cards, and smart cards would have still smaller memory, and so your JVM needs to have smaller footprint. The J2ME, what I had already talked about, the basic building blocks is your Java Virtual Machine, the libraries and profile. So, configuration part is the minimum platform required for a group of devices, and profile addresses specific needs for a certain device family, maybe a mobile phone. So, it will have an MIDP profile, a specific profile sitting on top of this configuration, and this complete thing is the runtime environment for Java on your devices. And on these devices, what you run, you do not run your applets or servlets, but what you run is called midlets. Applications, so these midlets are nothing but a set of Java code, compiled Java code along with the data, everything put together. So, what we say at the simplest level, a midlet is a class that extends abstract midlet class and implements methods like destroy application, start application and pause application, which is very similar conceptually that of an applet. Okay. But what is interesting here is that all the code, okay, that is all classes that is involved in an application as well as the data, everything is put together and put together into a jar file. Okay. And this jar file is actually what is to be loaded finally onto the target device for execution of the Java application. So, midlets are associated with a set of attributes, manifest attributes, which are part of jar file, because looking at manifest attributes, the system can know exactly what it can do and what is required to be done to support this midlet. And application descriptors similar to manifest, but outside jar file, these are application descriptors, that is another set of descriptors which are available, and user device can verify the requirement without downloading the entire jar file. Okay, so, it can find out what it does, then only it may decide to download the jar file. And there is this special files called JAT file, allows descriptor to be fetched from server using typical HTTP protocol. So, if you are using an internet connection, you can do that. So, a midlet typically is invoked by the application level software, an instance is created, that means, and then it calls midlet start application method to place it in what is called an active state. The midlet can be an active state, paused or destroyed. That means, when it is doing something, it is in active state. If it is waiting for an input, it goes into a pause state, else it gets destroyed. And state changes occur in response to user interacting with the software. In fact, today there are a variety of these kind of third party Java code which you can load onto your mobile devices and have added functionality. In fact, this is the basic framework for this kind of third party code to go into your embedded device. But Java, if we look at from a real time applications point of view, Java is unsuitable for developing real time applications, because fundamentally it does not provide you control over low level memory, okay, just like C. The GC, that this garbage collector can preempt unbounded amount of time Java threads. If it is preempt, then your deadline can be missed. This is a fundamental problem for developing real time applications. The scheduling of Java threads, although it can support multi-threading, the scheduling mechanism is not really completely specified. Okay? Obviously, to enable implementation across variety of OS platforms. Java does not provide high resolution time. What does that mean? Because if we are talking about a real time systems, then how do you specify your time or timing constraints? You have a mechanism to deal with time. And POSIX is a standards in terms of signals and other interfaces for your real time developments. This Java is not strictly conforming to that. So, classically Java is not really suitable as a real time programming language. Now, there is and if you look into it, this basic problem that of GC that I was trying to talk about, this may be your code which is getting executed and garbage collector comes in here and interrupts, so your deadline can be missed. So, there is a suggestion for a real time Java. Okay. And why we are looking at real time Java? Because there are also various real time programming languages, and real time programming languages, one example that is why we are looking at with reference to Java, because they are expected to have some special features to facilitate real time implementations. With reference to Java, what you find that it has got a new memory management models that can be used in lieu of garbage collection. Okay. So, the garbage collector need not preempt a process for an unbounded time. It requires access to physical memory. You have stronger semantics on thread and their scheduling. That means these threads and how they can be scheduled, because scheduling scheme actually tell you whether the real time constraint can be really met or not. And you should have a mechanism for asynchronous event handling. What is an asynchronous event? If an interrupt is being generated by a device, that is an asynchronous event, and there should be a mechanism to handle that asynchronous events. Okay? And you have the timers, ability to deal directly with the timers. These are the features which are typically expected of a real time programming language, and the real time Java do support these features, and it is under basically acceptance at various levels of standardization schemes. So, today therefore, what we have studied are general features of embedded software. We have analyzed features of programming vehicles for the suitability assembly language as well as high level language, and also examine features of software environment for embedded systems application.